Now we're going to use the mean value theorem to say something. Verify the function satisfies the hypotheses of the mean value theorem on the given interval. Then find all numbers c that satisfy the conclusion of the mean value theorem. Our function is f of x is equal to 1 over x, and the closed interval is 1 to 3. As a reminder, the mean value theorem has two hypotheses. F is continuous on a closed interval, f is differentiable on an open interval, and there's a number such that the slope of the tangent line is equal to the slope of the secant line. By the way, I didn't say this during the mean value theorem video. It was long enough already, wasn't it? What this is saying is that there's a point where the instantaneous rate of change, the slope of the tangent line, is equal to the average rate of change, the slope of the secant line. Anyway, I digress. Number 1, f is continuous. Heck, let's combine 1 and 2. F is continuous on the closed interval from 1 to 3 and differentiable on the open interval from 1 to 3 because it's a rational function, and we know rational functions are continuous on their domain, so we need to say something about the domain, whose domain includes the closed interval from 1 to 3, right? The only number not in the domain of f of x equals 1 over x is 0. So we've satisfied 1 and 2. Now we need a derivative, and we need f of b, f of a, and b and a. Of course, a and b are 1 and 3. F prime of x is equal to negative 1 over x squared using the power rule. F of 1 is equal to 1. F of 3 is equal to 1/3. So there should be a number c such that f prime of c, so 1 over c squared, is equal to f of b is 1/3 minus f of a is 1 divided by b minus a, so 3 minus 1. So negative 2 is equal to negative 2/3 c squared, which means that c squared is equal to 3, which means that c is equal to plus or minus the square root of 3. But hang on, we're supposed to be between 1 and 3. Negative square root of 3 is not between 1 and 3. So c is equal to the positive, I'll rewrite it, the positive square root of 3. I would encourage you to use a graphing utility to verify this for yourself. And I just realized that was much more easily said than done, so here it is for you. We have y is equal to 1 over x is the green curve, and then with c being the square root of 3, we have square root of 3 comma 1 over square root of 3 as the point of tangent c. The slope is negative 1/3, and so this purple line is the tangent where c is equal to the square root of 3, which is about 1.7. And then the secant line between 1, 1 and 3, 1/3 goes through the point 1, 1 and has a slope of negative 1/3. So here's the picture that goes along with this problem. And the next one is going to be pretty theoretical as well. We're given an equation, 2x minus 1 minus the sine of x is equal to 0. And we're asked to show that the equation has exactly one real root. And we aren't going to show it by solving it. We have a linear with a trig it's a pain to solve. In fact, I'm not even sure that we can get an exact answer out of this thing, or exact value, but we're not asked for that. I need to point out something about what the instructions say. We see the words exactly 1. Exactly 1 means it's really got two things embedded in it. At least 1 and not more than 1. So we're going to show that it has at least one root, and then we're going to show that it has not more than one root. For at least one root, we're going to use the intermediate value theorem. We've seen this in a problem in a previous set of videos. For not more than one, we're going to use Rolle's theorem. First, for the at least one root, we let f of x equal 2x minus 1 minus the sine of x. The reason we're doing that is we need a function for the intermediate value theorem, and it needs to be continuous. And f is continuous on the real numbers because it is the difference of a linear and a trigonometric function. Now I need to think of a number x where the f will evaluate to a negative number and then a positive number, And then because it's continuous, I'll know that there's somewhere between negative and positive where it's going to hit 0. So it looks to me like f of 0 is going to be -1, and I don't really care that it's -1. What I care is that it's negative. And then, I don't know, f of 10 is equal to 20 minus 1 minus the sine of 10. I don't know what the sine of 10 is, but I'll tell you what, it's between -1 and 1. Therefore, this thing is positive. I forgot to mention something about the domain of the linear and trigonometric function, in particular the trigonometric function. I should have said with domain R. Remember, 4 out of the 6 trigonometric functions have discontinuities. Now I can draw the conclusion that by the intermediate value theorem, there exists a C in the interval from 0 to 10 such that f of c is equal to 0, which means that the equation has at least one real root. Okay, so that takes care of that part of it. For not more than one, we're going to use Rolle's theorem. Let's remind ourselves of what Rolle's theorem says. It says that if we have a continuous differentiable function that equals the same output twice, then there's somewhere in between that has a zero derivative. Let's try to visualize what it is that we've just done. I'm not trying to say this is to scale, but we said that f of 0 was negative and f of 10 is positive, and by the intermediate value theorem, there's somewhere in between 0 and 10 where the function value is equal to 0. Now remember, what we're trying to do right now is show that there is not more than one real root for the equation. In other words, there's not more than one 0 for this function. Let's see what it would mean for there to be more than one 0. That would mean that this function would have to come back down and cross the x-axis, or it would have to come back up and cross the x-axis. In either case, if I have two different places that have the same output, then in between them, I would have a zero derivative, right? Whether it's over here or over here. Somewhere I would have to have a zero derivative. So what if I could show that there was no place where there was a zero derivative, right? So suppose we know that this is not true, or suppose this fails. Look at the function we're talking about. It's the difference of a linear function and a trigonometric function that has a domain of all real numbers. This is continuous. This is differentiable. We'll write that down in a minute, but we see that f is continuous and f is differentiable. If those two are true and the conclusion fails, then it must be that number 3 fails as well. Because look, if 1, 2, and 3 are true, then the conclusion will have to be true. So if I can show that there's no zero derivative, then I can show that there's not two places that have the same output value. In particular, I would show that there aren't two places where the function value is equal to 0. It's called a proof by contradiction. So I'm going to say f is continuous and differentiable on R because it's the difference of a linear and trigonometric function with domain R. Now, suppose, so with a proof by contradiction, you assume the opposite of what you're trying to prove. So suppose that there exists two numbers, A and B, where A is not equal to B and f of A is equal to f of B. Now I'm supposing this. Now we have continuous, differentiable, equality, then it must be that there must be a C where the derivative is 0. But, that's our favorite word in proof by contradiction, but with f of x being 2x minus 1 minus sine of x, f prime of x is 2 minus the cosine of x. And f prime of x is equal to 0 would imply that 2 is equal to the cosine of x, which has no solution. Thus, there does not exist a c in the entire real numbers such that f prime of c is equal to 0, which means because we already know f is continuous and differentiable, the conclusion failed. It must be the case that f of b does not equal f of a. So there do not exist a and b such that a and b are different and f of b is equal to f of a. In particular, there can't be two places where the function value is equal to 0. So the function has no more than one 0. So the equation has no more than one real root. If the equation has, let me try that again. If the equation has no more than one real root, and the equation has at least one real root, we can conclude that the equation has exactly one real root.